Okay, we're actually returning to a familiar problem here with this video. Back in our last unit in energy, we did a problem with a ballistic pendulum where we tried to figure out if we fired a bullet into that block and it went up, how high it should go up. And when we did that problem, it was actually going at 50 meters per second, and it ended up getting to a final height of 0.25 meters. So we're gonna do this problem again. When we did that one, I already told you guys there was a mistake that happened because of the loss of energy. But in this video, now that we know about conservation of momentum, we can actually solve this problem the right way. We're going to compare our answer a little bit and talk about how much energy was lost. So going through here, it's almost the same question. The only thing that I'm changing is I'm actually going to fire the bullet 8 times faster at 400 meters per second instead of 50 meters per second. Based on the way the math works out, you guys should already predict, or if we solved this the exact same way, we would predict it's definitely going to go way higher. It would actually, I think, go 16 times higher if things worked the way we did in our first video. But we're going to go through this problem now. And the first thing that we need to do is the step that we had to skip last time, which is the step where we actually talk about the momentum, the collision that happens here. So let's talk about this real quick. We have the momentum of the bullet, that's momentum bullet, plus momentum block. And then at the end, the bullet is going to be stuck inside of the block. So we're going to call that the momentum of the BB system, the bullet block system. So calculating this stuff out, the block is starting at rest, so it has no momentum. So it would just be the mass of the bullet times the velocity of the bullet equals the mass of the bullet plus the mass of the block. That's the mass of the whole system times their final velocity. So if I wanted to figure that final velocity out, I could just divide both sides by this total mass. So it would just be mass of the bullet times velocity of the bullet all over mass of the bullet plus mass of the block. So we can plug in some numbers now. That is 0.004 times 400 times 400 all over, this works out, I did this on purpose, 3.996 plus 0.004, that works out to be 4 kilograms. So that's easy. This is 1.6 over 4 kilograms, or 0. I wrote it down so I didn't have to check this halfway through. Yeah, or I didn't have to plug it into a calculator. 0.4 meters per second. All right, so that's how fast our system's actually moving at the end of this. It is important, or it's interesting here, to compare the kinetic energy of that bullet before it hit to the kinetic energy of the system afterwards. So before it hits, we have 1/2 times the mass of our bullet, 0.004 times our velocity, 400 squared. That comes out to 320 joules. Afterwards, it's 1/2 times 4 times 0.4 squared, which works out to be 0.32 joules. That is a significant and huge loss of energy. That was a huge, deliberate but huge error that we made in our first one when we ignored the collision that took place there. And I talked about in the video how I did this lab and I got it horribly wrong, and I kept getting it wrong, and I ended up getting like a -40 on the lab report. This is why, because it was not a minor thing that we ignored. Just like you guys wouldn't have known to ignore it in that last video, I didn't know it at the time, but now you do. So be careful when you're looking at collisions or when you're looking at a problem like this, to keep in mind that because that collision happened, you have to use a conservation of momentum problem, and then you can move it into the energy problem. So now let's go to that energy problem. The energy problem is we are going from the kinetic energy of our bullet block system to the final gravitational potential when it swings up and gets to that highest point. So this is pretty easy. It's just 1/2 mv squared equals mg delta y. Our masses cancel, and I can just solve for delta y. Delta y is going to be equal to v squared over 2g. Hopefully that's super familiar to you guys because of that drill quiz we did a few weeks or last week. So I can plug this in. The velocity is 0.4 squared, 2 times 10, and it works out that it only goes up 0.008 meters, which works out to be 8 millimeters. Okay, compare that to when we had it going 8 times slower, it went a quarter of a meter up, or 250 millimeters, or like 25 centimeters or something like that. Like a huge difference. And that's how big this energy loss is that happens when we have our this type of collision, which was a perfectly inelastic collision. So the goals for you out of this video, make sure that you understood all of the math that I did here. Make sure that you keep in mind the idea of doing a conservation of momentum problem first and then a conservation of energy problem after. And if you feel pretty good about those two pieces, then you should be good for this kind of thing on the AP exam. So thanks for watching and have a great night.